In this set of notes, we're going to introduce limits, and it's going to correspond with section 3.1 of the textbook. So we're going to be focusing on limits of a function. Previously, we discussed the limits of a sequence. Recall that we take the limit of a sequence a sub n as n goes to infinity if we use this shorthand notation. We could also consider limits of a function. And so when we consider limits of the function, we generally use notation like this. So here notice we're using f of x to denote the function, but remember the choice of the letter f is arbitrary. You could also have a g of x here, you could have an h of x, and then also the use of x is also arbitrary. X is usually the most common letter that you'll see, but y is also commonly used. And so here we're now going to consider x to be a continuously varying real variable that tends to a fixed value c. So as before, when we looked at the sequences, remember that we would have our index, which would be whole numbers that steadily increased. Well, here we could look at a continuous real variable, and so we're not just going to be looking at indexes. So we're going to start out with kind of a non-rigorous definition of limits. And so what is a limit? So one way to think of a limit is to consider dropping an ice cube in a glass of warm water and measuring the temperature with time. And so the question is, what is going to happen to the temperature as time passes? Well, if we have a warm glass of water and we drop an ice cube in it, we know that the temperature in that glass is going to change, but eventually over time, if we were to leave that glass of water sitting there for maybe minutes, hours, even days or weeks, we know that eventually, if the temperature of the room is not changing, that the temperature of the water in the glass will eventually level out to be room temperature. And so measuring that temperature through time, we can think of that as a limit. And so if we were to let time go on for long enough, eventually the temperature of that glass of water would be equal to the temperature in the room. And so here we have two different definitions of a limit. And so in the first one, we say the limit of the function as x approaches some constant c is equal to L. And what this means is f of x, or our function, will become arbitrarily close to L, that value of the limit, if x is close enough to c. So one way to think about this is x and c, those are both inputs to the function. So we're saying as the input x gets really, really close to some value, the output, which is f of x, is going to get really close to L. Now, one thing to notice here is we're not saying that x is equal to c. We're just saying as that input gets really close to c. And you can see that here in this alternative definition. So in this one, we say as the limit of the function approaches L for any sequence of numbers. And so here we're using the sequence of numbers to denote a sequence of inputs that we could put into the function. And we're going to allow that sequence of xi's to get close to c, but not necessarily equal to c. Then what we're going to see is the sequence of values of the outputs are going to get close to L. And so again, an important thing here is that we're not saying we're evaluating the function at c itself. We're looking at what happens to the outputs as the inputs get close to c. And we're going to look at several examples here, and you'll see in some cases that distinction is not important, but in other cases that distinction is important. And so limits can converge or diverge. And so if that limit is equal to some finite number, then we say the limit converges. And if it's not, we say that it diverges. And then additionally, when we say that x is close enough to c, we mean that x approaches c from either direction. And we could, if we wanted to, specify whether that direction be to the left or the right. If we don't specify left or right, then we mean that we're coming in from both sides. And again, we're going to see some examples of this. All right, so let's start out by looking at the limit as x approaches 100 of the function x over 10. And so what we're going to start out by doing is let's first look at what happens to the output of the function as the input gets closer and closer to 100. So to start out with, let's approach 100 from the left. In other words, we're going to look at some numbers that are smaller than 100, and we're going to get closer and closer to 100. So we could start out with x is equal to 99.9. We could get a little bit closer and say x is equal to 99.99, or even closer and say that x is equal to 99.999. So these are three potential outputs that are getting closer and closer to that value c that we're interested in, and notice that c in this case is 100. So now let's look at what the output would be for each of these three inputs. So x over 10, when x is equal to 99.9, would be equal to 9.99. X over 10 would be equal to 9.999 when x is equal to 99.99. And x is equal to 10, x divided by 10 is equal to 9.9999 when x is equal to 99.99. So notice when we're coming up from below 100 and we're getting very, very close to 100, we can see that the function is getting closer and closer to the value 10. Now what if we came in from the other direction? So what if x were equal to 100.1? Or x was equal to 100.01? Or x was equal to 100.001. So notice for all three of these, we're not equal to 100, we're greater than 100, but we're getting very, very close to 100. And so same thing as we did when we were less than 100, we can evaluate x over 10. And what we're going to find is we get values that are getting increasingly closer to 10, but not equal to 10. Should be one more zero there. All right. So this is a case where we would say that the limit as x approaches 100 of x over 10 is equal to 10. Now it does end up in this case, if we were to directly plug 10 into this function, if we were to plug 100 directly into this function, we would end up with a limit of 10. And so this is a case where we could have plugged in the value and would actually see the limit, but again, that's not always true. So let's look at another example. So here we're going to find the limit as x approaches 0 of f of x, where f of x is just equal to x. Right? So let's draw what this would look like. So I'm going to label my axes here. I'm going to have the lower bound be -5 on both the x and the y axis. And so here on the x-axis, I'm just going to have the value x. And here on the y-axis, I'm going to have f of x, which in this case is also just x, because this is the identity function. And so if we would plot this, if x is equal to -4, f of x is equal to -4. If x is equal to -3, f of x is equal to -3. And so this function is just represented by this line. All right. Now, we want to evaluate when x approaches 0. So let's, on the x-axis, draw a line where x is equal to 0. So the idea is we want to see what is happening to f of x as x is approaching 0. So in other words, what is the value of this function as we move this way and as we move this way? And we can see as we get closer and closer coming up from the left, and we get closer and closer coming up from the right, we are approaching the value 0. And so for here, I'll change my pen color back. We have that the limit as x approaches 0 of f of x is equal to 0. So both of these cases on this page are cases where we could have just plugged the value into the function and we would have gotten the limit value. But that's because as the function approaches from both the left and the right, we are approaching that value. This isn't always the case that it would happen like this. So let's look at a couple examples where if we tried to plug in the value, we would actually end up in trouble, so we need to do something else. All right, so we're going to look at the limit as x approaches 1 of the function x squared minus 1 over x minus 1. So first of all, notice that if I were to plug 1 into the denominator would be equal to 0. And we know that we can't have 0 in the denominator of a function, so this function isn't even defined where x is equal to 1. So instead, let's consider the function f of x equal to x squared minus 1 over x minus 1, defined for any value where x is not equal to 1. Right? So next, notice when x is not equal to 1, we have the following. We have that f of x is equal to x squared minus 1, which is exactly what we've got up above. And notice I can define it this way because, oops, should be not equal to. When x is not equal to 1, I don't have to worry about the denominator being equal to 0. And what I'm going to do is I'm going to use some factoring to help me here. Notice that the numerator can be factored into x minus 1 and x plus 1. And if I do this, I'm going to end up with some cancellation. Notice that this x minus 1 and this x minus 1 cancel one another. So I'm just going to be left with x plus 1. So the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to the limit as x approaches 1 of the function x plus 1. And we can do this because by that definition of a limit, we're not concerned with the point where x is actually equal to 1. We're concerned with what happens as x approaches 1 from the left and from the right. And so that's why we're able to do this and to say that these two are equal to one another, because again, when thinking about the limit, we're not actually concerned at that point where x is equal to 1. And so we could show that this is equal to 2, using either a table like we just did on the previous page, or using a plot. So here's another example. So in this case, we're interested in the limit as x approaches 4. But again, notice if we evaluate it at 4, the denominator, would be equal to 0, and we can't have 0 in the denominator. So this is a case where we can use conjugates to help us. And these are often useful when you see a square root in the fraction. So let's look at how we can use this to help. So we'll start out by defining f of x is equal to 2 minus the square root of x divided by 4 minus x when x is not equal to 4. So that way we don't have to worry about the denominator issue. Now next, notice that this is equal to 2 minus the square root of x, 4 minus x, and this is where the conjugates are going to help us, because I'm going to multiply this by 2 plus the square root of x divided by 2 plus the square root of x. So notice that this fraction that I'm multiplying by is actually equal to 1 because I've got the same thing in the numerator and the denominator. So all I'm really doing is multiplying my function by 1. So that's why these are equal. But the reason that this conjugate is going to help me is it's going to end up helping me get rid of this square root that's in the numerator, and it's going to help me with some cancellation. So we'll see what this looks like. So from here, notice that in the numerator, this is going to give me 2 squared minus the square root of x squared divided by 4 minus x times 2 plus the square root of x. And one thing that I want to caution you with, you may be really tempted to go ahead and multiply out that denominator. But remember that we're going to try to look for some cancellation to help us here. So to start with, I would not go ahead and multiply those out. Sometimes it's best to add in some additional steps and wait to multiply things out because that's going to help you see cancellation. So notice here in the numerator, this is going to end up being 4 minus x. And remember, since I didn't multiply out that denominator, I've got a 4 minus x here, divided by 4 minus x times 2 plus the square root of x. And so again, I'm going to end up with some cancellation. So those are going to cancel out. And so this is going to end up being equal to 1 over 2 plus the square root of x. And so what this ends up telling me is that the limit as x approaches 4 of 2 minus the square root of x divided by 4 minus x, this is equal to the limit as x approaches 4 of 1 over 2 plus the square root of x. And now, similar to what we did on the previous page, what I can do is either use a table or I can make a plot here and see what this limit's equal to. And it ends up that if you were to plug in 4 here, you're going to find that using the table or using a plot, you're going to approach that value. And so it ends up that this is equal to 1 over 4. And so in both of these cases, even though when we initially looked at it, the function doesn't actually exist at the value that we are approaching. So in this case, the function doesn't exist when x is equal to 1. And in this case, the function doesn't exist or when x is equal to 4, but the limits do exist. And so that's why we want to be very careful when we plug in values. So in both of these cases, not only do we have the limit, but the limit exists because it's approaching this finite value. And the first time it approached 2, and in the second time, 1/4. So next, let's look at some examples where the limit does not exist. And so in comparison, we can see what that would look like. All right, so in this first example, we're going to look at the limit as x approaches 2 of f of x. And here is what f of x is equal to. And so we have a plot of what f of x looks like here. So notice that this function is split into 2 pieces. It's defined for when x is less than or equal to 2, and it's defined for when x is greater than 2. And so here's what that plot would look like, and here on the y-axis we have f of x. So again, we're interested in evaluating this or looking at the limit as x is equal to 2. So let's kind of draw a dotted line here where x is equal to 2. Now next, notice that as we approach 2 from the right, we're approaching this point right here. And if we look kind of across here, what that's equal to, it's going to be approximately equal to 5. Whereas if we approach from the left, we see that the function is approximately equal to 3. So notice, since the limit from the right is approximately 5, and the limit from the left is approximately 3, in this case, the limit as x approaches 2 of f of x does not exist. But we could define the limit of f of x as x approaches 2 from either of our two sides. And remember that in order to have the limit itself, we need to approach it from both sides, but we have that right and that left-hand side limit that we could use as well. So here, if we wanted to look at the limit as x approaches 2 to the right, that is going to be approximately 5. And I think if the actual values, if we were to find what that value is, it's actually equal to 4.9 is what it ends up being. And then similarly, the limit of f of x as x approaches 2 from the left is equal to, it's 3.1 if we actually plugged it in and found the value. So again, this is a case where the right and the left-hand side limits do exist, but the overall limit does not exist. And that's because as we approach 2 from the two different sides, it's not equal to one another. All right, and we've got one more example here. And this example is also in your textbook. So for this one, we're interested in the limit of f of x as x approaches 0. Okay. And here f of x is equal to 1 over x squared. So let's just kind of think about what some of these values would look like. And so here's what the plot is. Let's think of a really, really small x that we could look at. So let's let x be equal to 0.00001. We know that that is a pretty small value. And then if we squared that, we're going to take 0.00001 times 0.0001, and so that number is going to be even smaller. So now we have a very, very small number. And we know that when we look at fractions, that the smaller the number is in the denominator, if we have 1 in the numerator, that this number, the output, is going to be very, very large. And so what happens here is as x gets very, very small, as it approaches 0, f of x is just going to get larger and larger and larger. And so whether we approach from the left or from the right, because notice in this case, we're squaring it. So if we approach from the left, all the negative values are going to turn positive. In either case, what is happening is we are just going to get closer and closer to 0 on the x-axis, but on the y-axis, we're going to go up to infinity. F of x is going to have no bound, and it's just going to get closer and closer and closer to infinity. So again, in this case, the limit does not exist. And we're actually going to look in section 3.3 specifically at limits that are equal to infinity. And so in this case, the limit does not exist and it diverges. On the other hand, we could have also looked at, and I'm just going to draw it on top of this plot, we would have seen the same thing if we looked at 1 over x. But if you looked at 1 over x, you would have seen something that looks like the following. When we come from the right-hand side, you would have went up and kept on going to positive infinity. But on the left-hand side, since we weren't able to get rid of that negative by squaring, you would have found that it went down to negative infinity. So it still would have diverged even without the squaring. All right. So here's the definition of divergent limits. And then it ends up that there are several different limit laws that can help calculate limits. And your book has many, many examples on this. So I'm not going to go through examples. Those are available in your textbook. And then, of course, if you have any questions for me, please let me know. And if you need additional examples, I'm also happy to provide those.